So what we're going to do today is basically go to Mihail's project page. So basically, I should maybe bookmark that at some point. I'll go to the research part. Exactly. So I'm gonna try to do one of these research um, folders. See if basically there's a bunch of things in here that they played with the original project. Try to kind of change some things here and there, and then investigating layers. And I just want to take a look at them and see if I can maybe arrive or understand how they got to the conclusions. But then I might wanna check out all these myself to make sure I have the same code. So, and that's different projects. So city projects. So if I go to here, I have Musty Thoughts. Plus I have Yellow Submarine, and then I should probably just clone these. How can I? Experiments Yellow Submarine. Interesting public research structure. So there's much more to this. But I think board technology doesn't exist anymore, right? Yeah. Let me clone that. So git clone this, and cool. So, and then basically, I don't know, I'll pick one of those. Let's see. So experiments. What is in guidelines actually? Research guidelines, software guidelines. Structure. Okay, it's for the repository. Software guidelines. Okay. Documentation. Experiments. So there's other stuff in here. D-Wave. Is TSP the traveling sales? No. Maybe. No. I don't know. Something with QIOA. Interesting. Okay. We can take a look at this. What is QKS? What is QKS? The Queen Catherine School. Quantum Kid is no QKS. That's not QKD. What? So, where was I? Yellow Submarine, exactly. So what are we gonna pick? What are we gonna pick? What are we gonna pick? I mean, I think this one here is just check reproducibility. I think what are these? What is the report saying here? Correct report. So we have checked how the algorithm behaves between different runs for the same set of parameters. We have used the following parameters. Unfortunately, the files generated during the training process are too big to store them in a repository, and we have not found a way to export the results from TensorBoard without a huge manual overhead. The following methods of evaluating cost have been used. Calculate the cost of all possible states, take the probability of all possible states, sum over all elements, divide by the sum of all probabilities normalization. This method corresponds to encoding where zeroing resulting state corresponds to 0 in the solution and all other numbers 1. So there's a bunch of observations. The result of for a given set of parameters were very similar. Just give me a second. I gotta. Let's see if I can resume. Sorry, I messed up with the. Oh, sorry for the mess here. So, the results for a given set of parameters were very similar. There were some differences in the final result, however they were rather minor. Also, evolution of the parameters was smooth without any major changes between the runs. Though it is worth noting that the final value of the cost function differed between runs. It has not always converged to the same value. Observation to the training process was very smooth. This probably due to the methods of cost function used. Even though these methods work very well, they are not very practical for larger problems on and outside of the simulator. There are, however, a couple of reasons for using this in this setup. It is an exploratory study. The argument fails with the most accurate value of the loss function. It will probably fail for the less accurate too. In a practical setting, we would have a set of measurements which gives us an approximation of the tensor probabilities of all states. The more measurements we have, the better approximation we get. Also, we don't need to calculate the costs of all the possible solutions. Much less smooth. Optimized. Remove normalization step from the cost function and we'll use method A. Oh, so there's perform element-wise multiplication. Sum over. What was the let me check. What was the previous method used? If Atom is going to open. So what was the point here? So this main goal of this search was to check how similar are consecutive runs of Yellow Submarine, Max got solver. The output of the algorithm is probabilistic since the parameters are randomly initialized. This might cause the algorithm to converge into very different solutions with every run, and hence a huge number of repetitions might be required to achieve a confidence that the result we get is reproducible. Okay. Code, TensorFlow problems. So open folder. So projects. Yellow Submarine. So example, Max got solver. What was the cost function here? Train and evaluate. I almost forgot how this looks like. Total cost. Is it here that's being evaluated? Calculate cost once. Prepare cost array. Loss function. Because this is the example. Adjacency matrix, constant C and D have to be chosen so that the eigenvalues of A are in the range. Interferometer matrix used for the circuit. I guess this could be basically, that's basically what it kind of defines the behavior of the interferometer, as in like whether you want the entanglement to happen or not and stuff like that, maybe. Here you prepare the circuit, train and evaluate, assess all solutions classically. End of the story. So it's basically train and evaluate is where you want to go. Train and evaluate. Training and evaluation of the circuit. Adjust the parameters of the circuit so the output minimizes. The value of the loss function after training is complete. The cost value of the final circuit parameter is evaluated. Adjust the parameters of the circuit so the output minimizes the value of the loss function. Yeah. Get the circuit parameters. Then gate structure. What does it do with this? Get circuit output. The cost tensor is then, okay, yeah, so the loss function is what calculates the I guess run costs tensor. I'm not familiar with TensorFlow myself, so I'm unless with Xanadu's language in here, so I'll really have to do wild guesses of what this is doing. So run the session, you get the circuit output, you get the cost value, return the cost value. Yeah, but where is this minimized then? What am I doing? Here, learn a train circuit. So the train circuit is already where the things happen. circuit learner. So I'm just basically trying to understand where is the VQE really happening here. So this is quantum circuit learner. I think this is the circuit learner. Quantum machine learning toolbox. So this module contains a class to train models for machine learning optimization based on variational quantum circuits. Exactly. The class extends TensorFlow's TF estimator class and adapts it to an unsupervised learning and optimization task. It hides the complexity of defining input functions, hooks, and configurations. The user defines a function that computes the outputs of the variational circuit, as well as the training objective, and specifies the model and training hyperparameters. Okay. And score. The TensorFlow Learner module has been designed for the training. But what's the point of... So, what's the point? Let me close that. So, what's the point of training that? In the example, you do these. You train. It feels a bit weird. Matrices. That we call this training, but I mean it makes sense actually, because you're training it on you're training it on one example, and so it's not training in the sense that you're training it against an actual known set of data. You're just training by just running the VQE. That's what you're doing, and then train evaluate circuit. Okay. So this is happening here, train circuit. Okay, so I mean this basically black boxes everything, so it encapsulates the actual it's a sharper parameter, train circuit. Run circuit, get the outcomes when running the circuit with the current circuit parameters. Okay. So nothing to, yeah. So that basically black boxes everything. Anyway, I was trying to. I actually wanted to open folder. I wanted to open the public research folder. The public research folder, and basically go to the reproducibility. Because so here we have a main and we have a runner, so we have actual. So we have an actual number to base. What is this? Run single test. Main learner parameters, training parameters, gate structures. What is all this doing? So due to some problems with resetting values of tensors in TensorFlow, in order to run several consecutive runs, you need to use the runner script instead of the main script. Okay. So if I use the runner script, so basically public research, I'm feeling super slow and sluggish today. Experiments. Yellow submarine. What is in here? Check reproducibility. Paste. Check reproducibility. Copy first. Paste. Okay. So, and we set the runner. So Python runner. The number of runs to perform as an argument to the runner. Okay. We're gonna do, let's just say 5 rounds. 5 runs. Let's see what happens. Let's see if that works. Meow. Check reproducibility. Starting 0, so that's kind of, I guess, the first run. There seems to be some. Okay, those are just warnings. What is it supposed to? What is it supposed to outcome though? What's the outcome supposed to be? Starting training parameters, cost, all the probabilities, cost. What is this? I want to close this. So there's an actual. So it's going to actually create some files. Interesting. Very large files. Cancel. Those are very large files. I'm curious how did he get the so I'm actually doing 5 runs and they're probably like 400 runs. Have they plot the loss d magnitude, whatever that is? Okay, so this is. Yeah, but why does it take so long? I mean, are they doing really like oh yeah, sorry, I wanted to compare the cost function. That's what I wanted to do. So I wanted to compare the cost function between these and but maybe they didn't change it actually here. Yellow submarine. Build the circuit. That looks like there's a bit of a different. So that's the loss function versus where's the loss function So here the loss function basically is cost tensor, weighted cost tensor results. So constant multiply, reduce the sum, multiply, and what have they done in here? If use reduced probabilities, else they do that. So he's change the way the loss function is calculated. Calculate the cost of all possible states, take the probability of all possible states. Perform element-wise multiplication, sum over all elements. So let's anyway, let's stick to the observations. Let's see what can we do with the time that we have. 400 steps was not enough to converge for most cases. I mean, did this do anything? Oh man. Model diverged with loss, not number. Starting 1. That's weird. That is weird. So I'm getting not a number, like none lost during training. Is this something? Doesn't look good. Doesn't look good. Doesn't look good. Observation 1, the result, it's still running. The thing is, starting 1, I made like 5 runs, okay? So the result for a given set of parameters were very similar. There were some differences in the final result, however they were rather minor. Also, evolution of the parameters was smooth, without any major changes between runs. It is worth noting that the final value of the cost function differ between runs. Doesn't always converge in the same value. The thing is, I'm missing here, how many runs have you done? And I forgot to check whether this is the ones that are actually being used in the code. And it should be here in the main. And it should be this in this. Oh, steps 400. Maybe that's why it takes so long. Cutoff dimension 17. Okay, so here's steps 200. We have checked how the algorithm behaves between different runs for the same set of parameters. We have used the following parameters. That's why it takes so long. I mean, it sucks that it's not. So matrix divisor 3. Oops. Sorry. Can I don't save the changes? The interferometer matrix. What is the interferometer matrix, by the way? Interferometer matrix. So, because this is, what's kind of weird is it is given as parameter to the circuit learner, right? Matrices, run single test. No, it's given, sorry, it's given to the maxcat solver class. Matrices. Okay. Interferometer matrix is as a parameter self, and where is this then used again? Aha. Okay. It's passed as a parameter to the interferometer. Because here basically there's something else, which is a Takagi or whatever. The Takagi thing here. Interesting. The interferometer matrix. And what does these do then? How are the runs going? Still in run 2. Okay, so the first the run 1 does indeed give us something, a cost, total probability, and those are solutions? I guess so. Or what? I think so. Let's see. So I was trying. For some reason, I think that doesn't look like that in the main. So what's is the build circuit? Oh no, it's the same. Yeah, interferometer. So Xanadu. No. Interesting. Interferometer. So is a service application that simplifies optimization. Yeah, but then that's how can I? Okay, so is it strawberry fields? Is it if I do interferometer? Okay. How can I just find the documentation about the actual interferometer matrix? I want to know what the matrix is. What that matrix is. Boston sampling proposes the following quantum linear optics scheme. An array of single photon sources is set up designed to simultaneously emit single photon states into a multi-mode linear interferometer. And that's clickable. Oh, come on. That goes to Wikipedia. The permanent of a matrix. So the sampled single photon probability distribution is proportional to the permanent unity. A submatrix of the interferometer unitary. In quantum linear optics, the multimode linear interferometer is commonly decomposed into two-mode beam splitters, BS gate, and single-mode phase shifters, R gate, allowing for a straightforward translation into a CV quantum circuit. For example, in the case of four-mode interferometer with an arbitrary. Okay, so this is the. So basically, an interferometer can be tweaked, as in like what it actually really does to the Q modes. Research and contribution, introduction. Is this Blackbird? Sounds like it looks like it is. Quantum operations. I'm just like, can I not just find the damn class? I just want to find just the class, like the specification. Okay, so we're in Okay, so it seems like the run we also run problems with this with the run into problems with the second run. Model diverge with loss none. Is this a TensorFlow thing? Stack Overflow. Oh yeah, it seems to be a TensorFlow. An error. I always get this problem every time when training translation models with my own language pair. I have searched the issue. When training on GPU, the error is often caused by a SOT max that's getting a symbol larger than the vocabulary size. Please train on CPU for a few steps. The error message is much better. I suspect that in your data there are symbols larger than the vocabs. Okay, that doesn't help me. Perhaps the general question, but can anyone explain what would cause a convolution to diverge? I am using TensorFlow. Okay, so this basically is telling me that it's diverging, that it's not converging, or what? Lots of things I have seen make a model diverge. Okay, so it might be indeed a this might be indeed a thing of the parameters. So if I go to pub, because I kind of realize the steps is 200 here. There's an observation later on that says 400 steps was not enough to converge for most cases. Okay, so we probably confirmed observation 3 right now. That's where they left it at 400. It was not enough to converge for most cases. So that's not an error. It basically says that the model is not converging. So okay, so then we've got the run 3. Cost is minus 0.933 versus minus 0.477. Okay, and the solution is all ones, and in this case, yeah, still the same. And then 0.111. Okay, that's kind of the third one in this case. Starting the run 4. I mean, I don't know if I have to wait until all the runs are finished, but we basically, okay, now I get it. So this is the 400 steps is not enough to converge for most cases. Most tests were performed with a learning rate 0.1. However, when this was increased to 1.0, the training process was much less smooth, and the characteristic oscillations appeared for almost all the parameters. I don't know how to get all the graphs. The figures, the magnitude loss. Okay. The S magnitude. The S phase. What are these? The D, the displacement. Is this something with the displacement to do? And the angles, or and each colors are the different runs, or what? The S magnitude. I'm missing one of those things. I need to know. Maybe Michal can help me out on this a bit, or can give me a hint on those. I'm basically missing what those figures really mean, because in the report there's nothing. So there's an old report. Why is it invalid? Agency matrix. Okay. So here there's like all these different huge files, Maybe those are taken. Very large files. I'm a bit afraid of doing that. Okay, but basically, I think no. That's what is that? Close that. Maybe then those are files and used graph. What is this? This is. Don't want to break this. This is too big. Checkpoint. Okay. So this is data being logged from the runs, and just simply need to understand what is the data that's being logged. In here, training parameters, cost, total probabilities, values, and this is cut off. Outputs raw, outputs num, circuit outputs clipped. I'll be interested in try to be able to reproduce the figures. That this is what I would like. This is what I would love to do. Try to reproduce the figures. If I'm able to do that, I'll be really happy. Not in this video probably, but okay. So I think I'm done for now. Basically, I got a rough. So I'm still of course not. I think I still didn't get the preparation of the A matrix, of the matrix A. That's something still that I can try to understand better. But I understand how this more or less at a code level works. And the runs exactly. Yeah, cool. There's a bunch of other observations like so parameters of the curve gates were almost always changing extremely slow. It says like how do you get those observations? How do you reach those observations? It's because you are able to take a look at the data at the inside. So that this must be somewhere in here. So in the logs, right? Let's try this. Let's open the big file. Oh yeah, not that big. A global step. Okay, so I should. Maybe there's just a way you can, with TensorFlow, generate those. Yeah, that's a huge file. Oh my god. Complex. Okay, so here you've got raw data, and probably you can process that to d complex value. And this sounds like, what if I find d magnitude? D magnitude. 144 values found. Yeah, and okay, so those are the things used to plot the figures, I think. But maybe there has to be a way to get those plots just using the TensorFlow. So I'll explore that in my next video. Just basically want to be able to want to kind of compare my results with Miha's results, but at least I can confirm observation 3. Cool, perfect.